And let me bring back the slide share. Okay, and we'll keep going. Yeah, well, so just the last question, comment there in the group chat. Can we call machine learning as just iterative minimization because training learning is an overstatement? Yeah, different fields use different language. I think in the statistics and applied math community, this would all just be called optimization. And I think a lot of this is just an artifact. The language we use is an artifact of which specific group of researchers are studying the problem. So if you're talking about AI, then the words like training and learning are the ones you encounter. And that's kind of the reason for that. Statisticians, applied mathematicians might just call this optimization. So of course, the term optimization is also in use in the ML community, but it's people use different terms for the same thing effectively. Okay, so automatic differentiation, that's been sort of the availability of these packages like TensorFlow and PyTorch has been one big driver of success in machine learning because it's democratized a lot of how we do this work. It's allowed us to build these models at scale, to quickly train them with a minimal, without having to reinvent the wheel every single time, and allowing us to explore more complicated architectures without worrying about how we might train them, right? The other areas of big progress has been in our understanding of how exactly learning actually works, the process of learning itself in these deep networks. Something that was maybe underappreciated until the mid to late 2000s, but now we have a bigger handle on. And this has been, I would argue, just as key as the availability of automatic differentiation packages, right? So so in this section, I'm going to give you a quick overview of some sort of important results in the last 10 to 15 years, right? So the first big advance has been in our understanding of how the choice of your activation function impacts learning. So remember I mentioned the sigmoid function earlier. And this was the default choice for many decades, right? So from the early days of neural networks right up to the 90s and 2000s, that nonlinear activation function, people just used the sigmoid. And the reason for that was because, again, remember, this came from the inspiration for neural networks came from biology. And we talked about how neurons tend to be in either, they're either firing or not. So the idea was, well, ideally what we'd like the activation function to be is like a step function. But this discontinuity meant if you were deriving those analytic gradients, you couldn't backpropagate through this nonlinearity because the function becomes non-differentiable at this point. So the sigmoid was seen as kind of the continuous approximation to that step function. So it became a default choice and became a popular one. And of course, another alternative is the tanh, which has a similar shape, right? So both of these are popular choices, but they create headaches when you go to deeper networks. And this is something, like I said, that was underappreciated until we started building deeper and deeper networks. And what is the problem with using these activation functions when you're building very deep neural networks, like the ones with hundreds of layers deep, like we were looking at a little earlier? The problem is in these zones, right? So where the curve starts to flatten out and the derivative becomes very, very close to zero. I mean, the derivative is bounded by 0 and 1 everywhere for both these functions, right? But particularly in these saturation zones where the function saturates, it's basically 0, right? And what does that mean? Well, think about it. If I have 100 layers deep, I have a neural network that's 100 layers deep. So what ends up happening is that as I'm doing the backpropagation and I start computing these derivatives, if the things I'm multiplying together using my chain rule are all in this range between 0 and 1, and I keep multiplying and I keep multiplying and I keep multiplying, and I do this hundreds of times, it's not long before your gradients basically all just go to zero, right? And especially if some of your units are starting to saturate because their inputs are getting too small or too large, so they're ending up in this regime, when the gradient tries to flow back through that one nonlinear activation, it will basically go to zero, which means, yes, you may get some learning in the very last layers of your neural network, so the layers closest to the output where the gradient signal is strongest, where you're doing fewer multiplications. But by the time you get to the earliest layers in your network, the one closest to the inputs, you've multiplied so many things, so many small numbers, that by the time you get there, the gradient is basically zero. So you end up making very few adjustments to the weights in those early layers. So the learning there in those early layers basically slows down to a crawl, or there may be no learning going on at all. So this is something known as the vanishing gradient problem. Right. So this idea that the gradient flow, when you do the backpropagation through your network, may not be well behaved, and you may end up not having a whole lot of signal in those early layers. So one of the big innovations to address this, so this was a question in the chat as well, was the introduction of a different nonlinear activation function, something known as the ReLU. So this is a, what's going on here? So this is a different activation function. So ReLU for rectified linear unit, which has this form, right? So as Morten points out, introduced around 2010, but really popularized in 2012 with that AlexNet paper, which brought together a number of these innovations together in one paper. But essentially, it has a gradient of 1 in this regime. So if your x is positive, your gradient is just always 1, and there's no saturation on that side. But below, for negative x values, it flattens out and becomes a 0, right? And people found that if you used this activation function in deeper networks, this is much better behaved, mainly because it doesn't saturate in both directions. Now, you can still run into issues because of the saturation on this end. And this will happen sometimes with ReLU networks, that some of your ReLU units get stuck. But what people found is also that a lot of these ReLU networks are able to escape these saturations on their own if given enough time. So unlike the tanh and sigmoid, where saturation is kind of a kiss of death, you never really escape from it. With ReLU, for some reason, we're able to escape this saturation zone, right? People have since made a few small tweaks to the basic ReLU. So for example, instead of making the gradient completely 0 in this region, there's something called a leaky ReLU. So leaky ReLU, which has a very gentle gradient in this negative x regime. So might have something like 0.01x, for example. So where if I take the derivative, it's not going to be 0, but it's going to be a very small number. So the important thing is you still need a nonlinearity, right? But it doesn't have to saturate necessarily. And this leaky ReLU, there's been some work showing that this is maybe a little better. And there's a few other options as well. But as a default, if you're training a deep network, a ReLU is not a bad place to start, and you don't have to mess with it unless you have a good reason to. Yes, the derivative is not defined at 0, but as someone else pointed out, you rarely get exactly 0. And in practice, I think the automatic differentiation engines just pick one or the other. So just pick a derivative on one side or the other and go with it. And it doesn't really have as much of an impact on your training, no appreciable impact. The other thing the ReLU has going for it is the fact that the operations it performs, the stylus trips me up sometimes, my apologies. The operations it performs are actually fairly simple, right? You just take the maximum of 2 numbers. And computationally, this ends up being really, really inexpensive as well. So compared to both the tanh and the sigmoid, which need to evaluate the exponential function and also do this floating point division, both of those are expensive things, relatively speaking, compared to simply taking the max. So the ReLU also gives you a computational speed up in that sense if you're training really large networks, because remember, you might be doing this millions of times depending on the size of your network in a single forward pass. So this is so it gives you benefits in all sorts of other ways. There are still some niche cases where you might continue using these two activation functions, though really people have for the most part retired the sigmoid altogether, and it's really just not used at all anymore. If you need one of these, then the tanh is recommended as the one to use, mainly because it's centered about 0 as opposed to the sigmoid, which is centered about 0.5. And the reason that's a nice property to have is because it makes the optimization process a little more well-behaved, right? So I won't get into the details of why that is, but if someone is curious, we can talk about it another time. So the one place where you might want to use a tanh is as the output layer. And that's because, well, you're not embedding it in all these hundreds of hidden layers, so you're unlikely to run into this vanishing gradient issue. And the reason this may be a useful output layer is because if you're doing, say, a binary classification problem, then applying a tanh to the output of your network gives you a very natural binary output, right? So you can just interpret the output as one of two class labels. But aside from that, in deep networks, tanh is seldom used. You will seldom see it anywhere outside of the output layer, right? So activation functions, we've learned a lot about them. Like I said, the ReLU was a major innovation at the time it came out in 2010, and it really does seem to help if you're training a deep network. This is a good default choice. Okay. The other area where we've learned a lot in the intervening years is how to initialize your network. So what does that mean? So remember earlier when we were talking about the computational graphs and the optimization, I said just assume these weights have been set to this value and we'll go from there. Well, when you start off, you need to set your weights to something, right? You need to initialize your weights to something before you start the learning process. So why do you, so how do you do that? So an intuitive thing to do is to set all the weights to just 0, right? Seems like a straightforward thing to do, but this is actually kind of really bad if you think about it. And someone actually brought up this issue a little earlier, and here's why this is a terrible idea, right? So imagine I initialize my network, and let's say, for the sake of simplicity, we'll just say it's a fully connected network, right? So network architecture doesn't really matter, but let's just say, so these are my inputs, right? And let's say all the weights are 0. Initially, every single weight, I set it to 0. Why is this a bad idea? Because, well, think about it. If I now do a forward prop through this network, the inputs all get multiplied by 0. So the output from both of these neurons will be the same thing, which means when it's time to do the back prop and update all these weights, identical gradients are now going to flow back through every single one of these weights, which means every single weight will get adjusted by exactly the same amount in exactly the same direction, right? So in effect, every neuron is going to end up computing the same thing and get adjusted in exactly the same way. So it's like this neuron is basically just a clone of that neuron. You just have a bunch of redundant neurons in your network. So you might as well have just thrown away everything and just kept one neuron and you have the same thing. So you don't really have a neural network at the end of the day, you have one neuron. So this is actually a really bad idea. So you don't want to initialize your weights to 0, right? So the key insight then is you don't want to start off at all 0, because when you start off, you want every neuron to compute something slightly different from each other so that the back propagation will move them all in different directions. So you want to break that symmetry somehow. And the intuitive way to break that symmetry then is, well, set it to random values, right? Well, and this is how this was done for a long time. So from the earliest days of neural networks to say the early 2010s or so. We would just set them to small random values, and intuitively this makes sense. You're just trying to break symmetry, and this is a reasonable way to break the symmetry. But there's some subtlety here too. And to see this requires a little more thought. So let's say I have, again, a neural network. And typically something that's done is when you feed in data to your neural network is to condition your data so that it's nicely behaved, right? So these x1 through x3s, you wouldn't just feed in the raw features. You might do something like standardization. So for example, you might scale every feature by subtracting the mean and dividing by the standard deviation so that every feature looks like a standard Gaussian. Right? And the reason for doing that is because you want some features on like very large scales and some features on very small scales, because if you do that, then the optimization will kind of spuriously focus on those very large features, because that's where the majority of the loss will come from. When in fact, you may have no a priori reason to give more emphasis to one feature over another. So standardization or normalization is a nice way to deal with that issue and put every feature on the same scale so that the optimization proceeds nicely, right? So if every single one of these features has a variance of 1, let's say we similarly initialize all our weights to be standard Gaussians as well, right? Which means let's now think about what activations on the other end are going to look like. So all of my inputs have a variance of 1. All of my weights have a variance of 1. But let's consider the variance of what comes out of this, say, one neuron, right? It's adding up a bunch of random variables, which if we assume them to be IID, we add up a bunch of random variables with variance 1. But that addition and aggregation means that the variance of the thing that comes out is going to be much higher. Right? So the variance of the activations of my neurons is going to be much higher than the variance of what came in. And why is that a problem? So remember that we have this recursive structure in our neural net, right? So the output of one neural net is the input. The output of one hidden layer is the input to some other hidden layer. So you can almost think of, if we sort of draw a border here, what you can think of this as is you have a bunch of inputs feeding into some smaller neural net here, which means these can be treated as the inputs to some smaller neural network. And since the variance of the activations of these neurons is much higher, all this nice conditioning work we did here to make sure this thing was nicely behaved has instantly been destroyed, right? Because the variance, because I'm not paying attention to the variance of my outputs of my neurons. And if this keeps getting ignored downstream, then the problem just gets worse and worse, right? So what that ends up happening is bringing us back to the same problem we were just looking at a second ago, where the activations start blowing up. Your squashing functions end up saturating. And now on the backward pass, you're again running into the vanishing gradient problem. And this will be a problem even with the ReLU. Right? So you end up with the vanishing gradient problem again. But we already have the key insight, right? Which is, yes, we should normalize all of these, but maybe we should be more careful about how we initialize the weights, because essentially if we initialize them to have the same distribution as the input Gaussian, then we have this growing variance issue. So maybe we should be a little more careful about the range from which we sample these weights, and we should be strategic in how we initialize it so that this variance stays roughly the same as the variance of the inputs, right? And that was the key insight. So this was an important paper, I think in 2010, by Xavier Glorard and Yoshua Bengio. who studied this phenomenon, and they had this insight that, okay, when you're building these deep networks, one good thing to aim for is to keep the variance roughly the same. So whatever variance you have coming into a hidden layer, you should roughly try to reproduce the same variance going out. And you can do a little bit of statistical analysis on this and quickly derive some expressions for what this range should be. And there's a few variants here, but essentially what it ends up depending on are two quantities I'll call n in and n out, which is the fan in and the fan out of every neuron. Meaning how many inputs are coming in to a given neuron, which kind of makes sense because you add those up and that controls the variance of your output. So it makes sense that the fan in matters. The fan out matters in a similar way, but if you repeat the analysis going in the other direction, so when you're doing the back propagation, you want to reproduce because the inputs and the outputs get switched. So essentially, you can repeat the same analysis, but just going in the other direction. So taking both of these things into account ensures that you have good signal flow when you're going forward in the forward pass, and you have good gradient flow going in the backward pass. So we have a number of initialization schemes based on these ideas. So the 2010 paper I mentioned by Xavier Clorot and Joshua Bengio, their initialization scheme is now called Xavier initialization because of this reason. And in their paper, they were analyzing tanh and sigmoid networks because ReLUs hadn't had their big breakout moment yet. A later paper from Microsoft Research, I think this was in maybe 2014, repeated their analysis for ReLU networks, and they came up with a slightly different formula, but it still depends on fan in and fan out. If you are interested in the details, I encourage you to look up what those terms are, Xavier and Hay initialization. The good news is TensorFlow, PyTorch, all these packages are already aware of these results, and these are the defaults used. The appropriate defaults get used anyway, so you don't have to worry about this, but it's just something to be aware of, that this is going on behind the scenes. Right? So clever initialization seems to have a huge impact on how smoothly the optimization goes. All right. Okay, so this has been, so automatic differentiation, that's been one game changer. These deeper insights into the dynamics of how the learning proceeds in these deep networks, that's been the other game changer. The final piece of the puzzle has been optimization methods, right? And I've sort of skirted around the issue repeatedly, and we've talked about gradient descent, but we've actually have sort of better tools at our disposal. They still depend on gradient descent, but with a few more bells and whistles. And this has been maybe the third other major advance. And of course, there's also the issue of hardware advances and big data, but those are not, those are just kind of givens, right? There's nothing interesting to talk about there other than, well, that happened. Here, there's actually like scientific and mathematical insights we can discuss. So optimization. The workhorse is gradient descent. So this entire discussion has been predicated on the fact that we're using gradient descent. Though I will point out that we don't, in the machine learning community, use traditional gradient descent or what is known as batch gradient descent. So your traditional formulation of gradient descent is if I have my design matrix, right? So a whole bunch of training examples, and the way we would implement gradient descent is pass every single example through your model, compute the loss on all the examples, right? And then compute this gradient term so that you figure out the direction in which to update your weight vector, right? But if you think about it, if we are dealing with modern data sets, which may have millions of examples, this is a non-starter. You can't wait to compute the loss on every single example in your training set, because if I have 10 million examples, I'm going to be spending hours just doing the forward pass and computing just the predictions on every single training example. So before I even compute the gradient, I'm going to be spending hours just computing the gradient so I can take one update step. So this is going to be a huge time sink. Second, the data sets are so huge, millions of images, for example, that it's not all going to fit in memory. So you couldn't do it even if you wanted to. And thirdly, when you have such a large number of examples, it's inevitable that you're going to have some redundancies in your data. So what do I mean by that? Examples that are very similar to each other, or even repeated examples, right? Which means that really calculating this gradient this carefully is a waste of time, because in many cases you are repeating the calculations on the same variables over and over, right? Okay, sorry, I just, is everyone still there? I guess the chat has gone a little quiet, and I just want to make sure that I'm not talking to an empty room where I've been cut off. Okay, good. I was a little nervous there. All right, excellent. So batch gradient descent, not a good idea. Basically intractable, right? If you have a large enough data set, and it's just too slow. You can't be waiting hours to take a single gradient descent step. So the alternative then is what is called stochastic gradient descent. So we're not going to wait to compute the gradient on every single example. Instead, here's what we'll do. We'll maybe take the first, we'll extract, say, maybe the first 32 examples, or maybe the first 64 examples. And again, powers of two thing, but again, there's a deeper reason for this, and this is hardware alignment. So when you're doing GPUs, it turns out that this helps, right? So so we would extract the first 32 examples, and what we would do is go ahead and compute the loss on just these 32. So make predictions on the 32, compute the loss on the 32, and go ahead and make this update anyway, right? So we're not computing the gradient with respect to all of the examples. We're computing it with respect to just these first 32, right? And I go ahead and take a descent in gradient space. And then we do it again. Do it for the next 32, do it for the next 32, do it for the next 32. So you just go through your data set in chunks, 32 or 64 at a time, until you've made a complete pass through all of your millions of examples. And we actually have a term for what one complete pass through the data set is. That's one epoch, right? So going through your entire data set in chunks of 32, and if you've made a full pass through the data set, that is considered one epoch. And typically you would train for many such epochs, right? So this 32 is, again, it's a free parameter. It's something you can choose and set it to something appropriate. This is called the size of your mini batch. And this overall style of doing these gradient updates on small mini batches of your data is what's called stochastic gradient descent. Now, how have we solved the problem with batch gradient descent by going in mini batches? Well, for starters, I only need to keep 32 examples in memory at a time. So I'm not going to run out of memory, right? I start making gradient updates right away, right? I don't have to wait to look at every single example before I update the weights. So the learning starts right away. And so those are two problems with batch gradient descent we've already solved. The flip side may be that you may be wondering, well, if I only take this narrow view of the data set and I start making these gradient descent steps right away, isn't there the danger that I may take steps in the wrong direction, right? Because after all, just taking a mini batch of 32, that can be very misleading in terms of the loss function, right? Like, what if I pick 32 examples that are like the ones I perform worst on, and now I'm going to make my model accidentally move in the wrong direction? This is true, right? So this will happen, but it turns out it's a feature and not a bug. So why is that? So if you think about the loss landscape for these deep neural networks, it's not nicely behaved. It's going to be something crazy like that, right? And remember, we're doing gradient descent, which means I initialize my weights to something random, and then I try to find the lowest point in this landscape, right? Now, if I do pure gradient descent, so batch gradient descent, and I take very careful steps and I only make downhill steps, then what will this do? Well, it'll walk down, walk down, walk down, find this local minimum and decide we are done, because every step I take from here takes me uphill, right? So we will conclude that we are done. Why is stochastic gradient descent better? Well, what will stochastic gradient descent do? Well, it'll start someplace and then make noisy moves, right? Which means sometimes the gradient will even take me uphill, which means even if I settle down in a place like this, I may go uphill and then be able to continue making progress. And these local minima are not as much of a hassle because, well, stochastic gradient descent means sometimes you'll take uphill steps. So the noise actually becomes something that helps your cause rather than working against it. So in fact, there are many good reasons to choose stochastic gradient descent. And this is kind of the workhorse algorithm now. This is sort of the standard in a lot of machine learning algorithms. And in fact, you can even, if you're curious, you can look up theoretical convergence guarantees. It turns out that you can actually have the best of both worlds. And if you actually have a convex optimization landscape, then it turns out the stochastic gradient descent will actually even converge to the same thing as batch gradient descent under some fairly reasonable assumptions. All right. So that is vanilla stochastic gradient descent. Now in practice, there are some minor sort of bells and whistles you can add on that will give you much better behavior. So the first enhancement is adding a momentum term, right? So what does that mean? Well, you're all physicists, so I probably don't have to explain to you how momentum works, but essentially think of it as, again, if you think of the optimization process, you're trying to find the lowest point in this landscape, and you think of it as a ball rolling down. Standard stochastic gradient descent doesn't have a momentum term, so it just will come down and may come to rest here. Maybe even the noise doesn't shake you out. A momentum term, adding it means your ball actually like gains velocity as it rolls downhill. Right? So if you do settle in a local minimum, maybe you've built up enough velocity to actually escape it and continue rolling down. Right? So essentially, if the gradient is consistent along some direction, then the updates will get more aggressive along that direction. Right? Question: won't stochastic gradient descent shoot out of a global minimum if the minimum is not very deep? Yes. So people have worried about that, but empirically, it turns out that if you have these steep minima and then you have other gradual minima, so people have done some analysis of the energy landscape, and it turns out that yes, these steep minima exist. Stochastic gradient descent seems to avoid them. And what's more, these end up being actually bad minima to find in your landscape. So we're actually not missing anything by skipping over these, because when you actually take these minima and then you try to generalize, look at the generalization performance of your model, when it's converged to one of those minima, it actually does worse. So these are actually minima to be avoided. So again, stochastic gradient descent appears to be doing the right thing. It goes to sort of these broad local minima that are more like this, which appear to be where you find good model performance. You will have some sharp minima like these, but those tend to be points in the landscape where your model has overfitted to the training data effectively. Right? The more modern updates to gradient descent with momentum are so-called adaptive gradient approaches, and there are two very common choices here. But essentially, these two algorithms are, so remember we always have this learning rate parameter that controls how big a step you take. Armisprop and Adam, in addition to maintaining a global learning rate, maintain a learning rate for every single parameter in your model, and they adapt those dynamically. So some parameters may change more quickly than others. So Adam and Armisprops keep around some limited history of the updates made to the various parameters, so that you may not use the same step size for every single parameter. And in practice, I think the community as a whole has arrived at some sort of consensus that Adam is an excellent default choice. And again, TensorFlow and PyTorch both have implementations of Adam. It's an excellent choice for your optimizer. It's fairly robust, it performs well, and it's a good sort of default choice before trying some of these other things. Okay. And finally, we'll finish up by talking about regularization, right? So the fact that neural networks are such, they are universal function approximators, right? So I think Martin may have alluded to this last week, but basically they can fit anything. But with that kind of power comes sort of the ability to also overfit your data. So to the point where you fit the training data so well that you've started your model is kind of starting to hallucinate. It's starting to see patterns everywhere, right? Where sometimes it's just noise. So you don't want that, right? You want to strike some balance between fitting the training data well, but the real sort of test of your model is how well it's able to generalize to examples it did not see during training time. So regularization is sort of the standard approach in optimization to address this. So add some controls to the optimization process that ensures that you don't overfit your data. So one thing you can do is something you've already seen last week, right? So adding an L2 term to your cost function. So this is essentially what ridge regression does. It adds a term of the form, so if your weights are this way, oops, sorry. So you take the 2 norm of your weight vector and square it and add this to your regular loss function, right? And then you try to optimize this whole thing. And the idea being that if I keep my weight small, then I'm also learning simpler functions. So that's the intuition behind ridge regression, right? So you can do this in neural networks too. Typically, you have some cost function that only cares about how you're doing on the training data, and then you add some auxiliary term to that cost function that ensures that you're trading off performance on the training data versus keeping the weights from exploding, right? So you can do this. It's called weight decay in the neural network community. Not really something that's done as much anymore because we have much better tools at our disposal, but this is something you can still do. Here is something that is neural network specific and is often very, very effective. So this is something known as early stopping, right? So it can also be thought of as regularization in time. What does this entail? So what you do when you're training your neural network, right? Remember, if you're using stochastic gradient descent, then you have many epochs of training. You go through the whole training data set over and over, right? What you can do is plot the performance as your model as you're going through those epochs of training, right? So in this case, we're plotting loss on the y-axis and the epoch number on the x-axis. And we're continuously evaluating our model on both the training data and some held out validation data that the model did not get to train on. So this is like an unbiased estimate of my model's performance, right? And notice what happens over time. Over time, I fit the training data better and better, right? But on the validation data, on the unseen examples, I make progress for a while, and then I stop making progress. And by the end, you have this enormous gap between the two. So this is, yes, so the validation is like test data. But typically, so almost in all cases, you actually break up your data into 3 segments. So you have training, you have validation, so you can do this, and then you have test data, which does not get touched at all until the very end, right? Your test data gets to be used once. The validation data may get reused over and over for hyperparameter tuning and so on. So it's being used for sort of a meta learning task almost, right? You're using it to learn things like when to do early stopping, what's a good learning rate, what's a good regularization constant. So since you're using it for training those parameters, those hyperparameters, in effect, the validation set is also contaminated. So you cannot report your final performance on the validation data, but you can use it for hyperparameter tuning purposes. And that's what we're doing here, right? Like in this case, what we would do is notice, oh, wow, things really started going haywire around epoch 10. So once I finish training my model for 50 epochs, I would generate this plot. Notice that epoch 10 was about where my model peaked, where there was a balance between fitting the training data well and also generalizing well. So I would just use the model as it existed at epoch 10, and that would be my final choice of the model. I would actually not use the model from the very last epoch, right? Of course, that involves checkpointing your model at the end of every epoch, right? So that's something you can typically do, is just save your model at the end of every epoch, so that when you're done, you can always roll back to an earlier moment in time and pick the model from that epoch, right? And TensorFlow, PyTorch, they have easy mechanisms that enable you to do that sort of thing. Yeah, would 5 be better? Yeah, it's a little bit of a subjective thing at this point, which one you want to pick. You could pick 5. I think the error on the validation set is even a little lower at 10 than it is at 5. So that's why I picked that one. Right. But several of them may be equally good. So this is not an exact thing, right? But eyeball it, and most of them would probably have roughly equivalent performance. But definitely you don't want to pick something from epoch 50. Right. Okay. A couple of really modern regularization approaches just to round this off. And these are specifically designed with deep neural networks in mind. So they really don't work for, say, support vector machines or linear regression or decision trees, because these really rely on you training a neural network. So the first one is something called dropout, which was, so remember that seminal 2012 paper I keep going back to, the AlexNet paper. So this was one more thing that they brought in that 2012 paper. So it was this integration of all these ideas, using GPUs for training, using large data sets, using automatic differentiation, using ReLUs, using a solid optimization method, and using dropout. So the reason that paper has like 90,000 citations or something at this point in time, right? It just brought so many of these ideas that were scattered in all these places together in one place. But the idea behind dropout is fairly straightforward. So if you have a fully connected network, the authors hypothesize that often in a deep network, what happens is neurons end up getting tightly coupled in the following way, where the behavior of one neuron becomes extremely dependent on the behavior of, say, one other neuron. So what they call a co-adaptation. And they said this is bad, because that means that your learning will end up being brittle, or it'll start overfitting easily if this neuron starts relying too closely on the specific values output by this one neuron. So how do we make this robust? So their proposal was, during training time, we'll flip a coin and start randomly dropping some neurons. Right? That's what these X's are. So when I'm doing a forward pass, I will flip a coin for every neuron and independently decide to drop some of them. And then I'll do the forward pass, and I'll do the back prop as well with all of these neurons frozen. So, and then on the next mini batch, I will flip a coin again, and a different set of neurons may get frozen out. So these ones that were frozen this time may come back on the next mini batch, and other ones may get frozen instead. So every single time you make a forward pass and a backward pass, your neural network loses some neurons and gains other ones. And this keeps happening back and forth, which means no one neuron can come to depend too closely on any other specific one. Because while this one may be available today, it may not be available tomorrow. So whatever you've got to learn, you've got to be a little more robust. Now, over time, people have started questioning whether this co-adaptation thing is the real reason dropout works. So there's still some debate about why it works. But what is indisputable is it does work. So it is, if you discover that your neural network is overfitting, this is a very effective way to deal with that. One doesn't really decide on the limit of the dependency. So addressing a couple of questions from the chat, you don't decide on the level of dependency, you just put in dropout. And typically the only parameter you need to choose is that coin flip probability. So set it to something like 0.1, 0.2, and tune it and see what works best, right? So you don't worry about whether your neurons are co-adapting or not. You just see that your model is overfitting and you decide to use dropout. Frozen, what do I mean by frozen? It's frozen on both the forward and the backward pass. So on the forward pass, this neuron will not contribute anything to this neuron's input. So notice all the links went away. So this neuron will contribute nothing to the prediction. So it should also, so it'll also not be a part of the back propagation, right? But the key thing is it's not frozen permanently. It's just frozen for this mini batch of 32 examples, right? So next mini batch, when I draw the next batch of samples for the next gradient descent update, I will flip my coins again. And this one, for example, may become active. This may become active. This may get frozen, and so on, right? Does regularization mean we do gradient descent simultaneously on both the training and the validation set? No, so we're doing gradient descent only on the training set, right? So I think this refers to the previous one. I'm only optimizing on the training set, on the examples in my training set. These red points are not based on optimization. They are simply my model's prediction on those points at that moment in time, right? So I don't make any weight updates based on these, right? I only make weight updates based on the points used in the training set. Okay, so that's dropout. The other major advance, and this is, I think, batch normalization is from 2016, so really very recent. But many people consider this the single greatest sort of advance in the training of deep neural networks since the original AlexNet paper. And again, it is, and the reason batch normalization, okay, so let's talk about what exactly batch normalization is. It addresses an issue we've already discussed. So we have sort of this deep network, right? So many neurons, and you go through layer by layer and train these. Now, notice what's going to happen over time as I train this network. Now, there's some distribution of outputs from this layer of neurons, which affects how these neurons behave. So when I do a backpropagation step, the weight adjustments I make to the neurons here is in some sense dependent on the distribution of inputs I received from the previous layer. But the problem is, as soon as I make this adjustment, this layer is going to get adjusted next, which means on the next forward pass, the distribution I saw the last time will shift, right? So it's almost like this moving target. Every single, as my neural network trains, the distribution of inputs that every layer sees starts shifting in time. It's not a stationary distribution because all the later layers depend on the earlier layers. So there's some complex dance going on there, which means that the distribution is like this moving target. It's constantly changing when this thing is trying to learn its weights, right? So how do we control for that? So this is the big insight from batch normalization. They suggest we should try to minimize this kind of what they call internal covariate shift. So keeping the distribution of input activations to a hidden layer roughly constant over time, so that it's not constantly, so that I make this layer's job a little easier, because it can trust that the inputs will roughly come from a same scale all the time. So some say fixed mean and standard deviation. And their fix is pretty simple, right? So it's exactly what you would expect. Basically, when this layer produces an output, we would just standardize those outputs to some target mean and standard deviation. Now I'm skipping over a lot of details there, and we need to be a little careful about how it's done. But intuitively, that's what's going on. And what you're essentially doing is keep trying to roughly hold the distribution of the inputs at this layer constant, so that this layer of hidden units has an easier time when it's learning. Now, as with dropout, there's actually a lot more controversy with batch normalization about whether this is the true reason it works. Some people have claimed it actually works as a regularizer. Some people think this internal covariate shifting is maybe overplayed, and that's not really the reason. And the reason batch norm works is it smooths out the optimization landscape a little better. Other people think that it helps address the vanishing gradient problem or the exploding gradient problem more directly. Whatever the reason, again, what is indisputable is it works and it gives you really good results. It controls overfitting. It lets you train with much higher learning rates. It lets your optimizer converge to better solutions. So there are many, many good reasons to use batch normalization, that it's almost sort of a good thing to just throw in by default and only remove if you have good reason to. So we have covered a lot of ground, right? But this brings us very close to sort of what the standard tools of the trade today are in deep learning, right? So it's a combination of many of these things. Like I said, automatic differentiation, hardware, large data sets, designing careful activation functions, being more careful about how you optimize, how you initialize your weights, and then these tricks for making the optimization process itself move slowly. So using things like momentum and adaptive gradients, and using things like dropout and batch normalization. So it's this enormous bag of tricks to call from. At this, so I think that's a neat summary of all sort of the major techniques that are in play in modern deep networks. Let me see how we're doing for time. I think we're a few minutes over, but maybe we have time for just like maybe we'll take questions for a few minutes and then pause before resuming at 11 a.m. for maybe a hands-on walkthrough. So looking at how to take all of this and translate it into code, right? So I'm gonna pause here and maybe take some of the chat questions. So question about batch normalization. Would you influence the learning for worse as it minimizes the changes you make, but it works? So I think the argument is it actually improves the learning, and that's why we do it, right? So the reason for batch normalization is you're trying to hold the distributions coming into a hidden layer a little more stable, so that this layer, when it's learning, it's not seeing a distribution that keeps jumping around in time, right? Rather, it stays roughly fixed, and maybe there's still a little bit of jitter, but it's roughly fixed in time. So this layer has an easier time learning from its inputs. And basically, we just repeat that argument at every hidden layer. So what we end up doing is normalizing the outputs of every hidden layer so that the input for the next hidden layer is roughly, is a little more stable, right? Another question about batch norm. Would you implement it between each hidden layer or just between a few? I don't think, yeah, so every time I've seen it, it's between every hidden layer. So it's typically, so if here is a layer, you would add a batch norm, and then you would then have a hidden layer, and then a batch norm, and then a hidden layer, and we just keep going, right? So you can go a little crazy fiddling with the architecture too much, right? So you want to simplify some of your design choices if you can. So this is typically how it's done. Oh, a quick question from Natalia to follow up on the earlier one about batch norm. Does it slow down the learning People have found that it's actually speeds up the learning because you can learn, you can use a higher learning rate and not worry about the optimizer diverging or anything like that. So it actually speeds up the learning. It slows down the computation, if that is the question. So because you're adding a few more, you're adding a little more machinery to your network. So the training will slow down a little because there's more ops, but the actual learning itself goes faster because you can train with a higher learning rate, which means you can get to your minimum faster. So on net, it's still a gain. Question from Anton, would you smooth your input data by averaging and removing noise in a pre-processing step? Yes, absolutely. So this is one of the things we'll look at in the hands-on session. Smoothing data by removing noise. So general pre-processing is a good idea. So for example, rescaling your features and rescaling the mean and the variance so that things are roughly on the same scale. In terms of denoising, it may not always be obvious how to do it, which is usually the challenge, right? So one thing you can do is remove outliers, right? So if it's obvious, so if I have a bunch of training examples like here, and they're all in this narrow region, and then I have a random training example there and a random one there. So you could remove these from your training data, right? But the question is, well, how do you identify those points? Because doing this will improve your model performance, but it may not always be easy to spot these outliers. In fact, that's a whole other learning problem in itself, learning to detect outliers, right? But if you can, if it's straightforward to remove noise, I can't imagine it hurts. Question from Paul, is normalization baked into the model, or would this be removed at the point where the model is working and we wanted to make predictions? You wouldn't remove, yeah, so there is something subtle about batch norm. So the details are escaping me at this point, but there is a difference between how you deal with the batch norm layer during training time versus test time. And there is a subtle difference about how it's handled. Unfortunately, I don't remember the details right now, but I'm sure if you looked up anything about sort of the implementation of batch norm, it should walk you through it. But again, the good news is you don't have to worry about these details because these are just implemented for you. And it's very easy to mess up the details. So I would highly encourage you to just not reinvent the wheel and use the standard TensorFlow or PyTorch implementations. Okay, one more question, and more of a basic question. How do we know how many hidden layers we need? You don't ahead of time. So for example, with that Google ResNet, the Google Inception layer, I think that's a few hundreds. I think that one of the top performing machine learning models is something called ResNet, and it has hundreds of layers. How did they settle on that? Well, you just keep adding layers and you keep generating learning curves like this one, right? So you could imagine that you generated this similar plot where you have depth, right? So how many hidden layers I'm using and my loss. And you will see something similar where the deeper I go, the lower my loss gets on the training data. And at some point, maybe on the validation data, it's tracking pretty closely, but then it starts to flatten out. And you would decide, okay, that is the point at which I'm willing to make the trade-off, right? Because adding more hidden layers is not cost-free. It's making your network bigger, it's making the computation more expensive, and so on. So, but if you want to be principled in how you settle on the depth, this is the way you would go. It's a hyperparameter that needs to be tuned. So you would need, Google or Microsoft level resources to be able to run these experiments in a reasonable amount of time. But even they, I'm pretty sure, take weeks to figure out how deep to go, because I need to train something that's 100 deep. Then I stop, and then I train something that's 110 deep, then 120 deep. And each of those may take days, right? But yeah, you're not just pulling a number out of air. That's the question. Okay, so maybe one final question. We'll take Daniel's and then we'll pause for a bit. Should you go from hidden layers with many neurons to fewer ones gradually, the opposite, or is there a pattern like that? No pattern like that, and you just try it. Yeah, I mean, I think it really depends on your problem. I think it's fairly traditional, at least in fully connected networks, to kind of have a funnel-like architecture, right? Where your earliest hidden layers will have the most number of units, and then you have fewer and fewer. And typically you don't have a whole lot of outputs, right? So typically this is fairly common for fully connected networks. For things like convolutional neural networks, which Michelle will talk about tomorrow, we'll see that the architecture is not quite this easy to describe. And there's actually a lot, many more things you need to worry about, right? So it doesn't have a straightforward explanation in terms of whether you have this kind of funnel architecture, but Michelle will have more to say about that tomorrow when we talk about CNNs. Right?
Hey, Raku, can I have a question?
Yes, very quickly. So maybe this will be the last one before we pause. Go ahead.
So what's the computation cost for a very large number of input? I'm not talking about the sample sets, but I'm talking about the like say you have 10,000 input nodes.
A large number of features, right?
There are more. Yeah, a large number. Not of features, but I was thinking about the PMT waveforms. So I want to input the whole waveform, which could have like a few thousand ADC channels there. That's a large input.
So
is that the main computational burden?
I mean, I think all of it matters. I think larger training sets will slow you down. More features will slow you down, but more features also has another effect, which is it also makes the learning problem harder. So learning in a higher dimensional feature space is harder than learning in a smaller dimensional feature space. So there's actually two different problems. It'll add computational cost, but it also makes the optimization harder. So both of those things matter. If you can get them under control, then you will see less issues, but sometimes there's no workaround around that. In CNNs tomorrow that we'll see, right, convolutional neural networks, one of the things that is so interesting about them is the fact that, okay, if you have a fully connected network, right, so that's mostly the architecture we focused on today. Notice that if I connect everything at every layer before, the number of weights I need to tune grows very quickly, right? So if I have m nodes here and n nodes here, that's m times n weights just for this layer. And if I have many of these, then you'd be summing all of those up. So you can have an enormous number of weights very quickly. One of the ways that convolutional neural nets get that deep without this number becoming intractably huge is the fact that they don't actually do fully connected layers. The connections are a little more sparse, and they're a little strategic about what gets connected to what. So the number of model parameters doesn't quite blow up as much as you would fear. So a 150 layer deep CNN is not going to have as many parameters as, say, a 150 layer deep fully connected network, even with just a modest number of neurons at each hidden layer. So the number doesn't grow without control. But to address your earlier question, the number of input features matters. More input features means you will have a harder time optimizing it, but computational cost is also higher. If you have a larger training set, I think that's an easier problem to tame. You can always just throw away some of your training data, right? So, and train on less data. So if things are moving too slowly.
And also, is it possible to train both discrete values, like say, for example, you have a continuous energy variable and a particle identification variable. So you have particle identification 1, 2, 3, 4, And in each categories, you have different energies. Are you able to reconstruct in 2 different layers?
Yeah, unfortunately, we're now talking about physics, which is well outside my wheelhouse. We'd have to talk a little more for me to really understand the problem. But maybe we can save that discussion for the workshop session later today, right? And where I'll have some more physicists for backup so they can help and jump in and answer these kinds of questions. I just moonlight as a physicist.
Okay, thanks.
All right, so I'm gonna stop here and stop the recording.